Okay, guys, let's continue with the remaining part of this chapter. Now I will focus on the consolidation and redesign, let's say, capabilities of additive manufacturing technologies. We said that in most of the additive manufacturing technologies, we can have most of the parts joined together. We can print the assembly as it is. You don't need to separate the parts, print them one by one, and then do an assembly operation. This is not actually a wise solution in additive manufacturing. Instead, what we do, we join these parts and try to build them in a single manufacturing operation. And we don't need to have special tools for all the parts. The single additive manufacturing process will be enough for the fabrication of the whole assembly. And later, since the assembly is fabricated as it is, you don't need to do any assembly operations. All these difficulties are eliminated. You don't need to use bolts, nuts. You don't need to have, again, fixtures. So they are all eliminated once you do a part consolidation. And obviously, the quality of the resulting assembly will be better than the quality of the assemblies you have in the conventional assemblies. And the problem is that the only problem is that you cannot easily do servicing, since if one of the parts is broken, you cannot simply remove it. You need to actually manufacture a completely new assembly. Here you see an example, a redesign case. This is the original design. We have, as you see, many pipes, some complicated mechanical structure to hold these parts together. We have probably some shafts moving inside this hole. But if you do a kind of a redesign, considering additive manufacturing technologies you have in your company, that will be the result. So what is the main difference? First of all, we are using less material. If you consider this gray and the blue regions, obviously the blue regions has less volume compared to the original design. Another thing is that this time we have smoother pipes. In the original design, we have such sharp corners, since with conventional approach, you can only have such kind of piping, but in additive manufacturing, you may try to actually have smoother pipelines, which will result in efficient flows, and this will increase the overall performance of your part. And now let's have a look at hierarchical structures. We said that this is another capability of additive manufacturing, and see how we can use this capability. We may have nanostructures, microstructures, mesostructures, they're all possible. We can add specific textures, since, as you know, some of your friends are working on textures. We can add some textures onto surfaces. These are all possible with additive manufacturing. We can have cellular materials. Lattice structures can be considered as cellular materials, and with the help of them, you can increase the strength to weight ratio of your part. With less weight, you can obtain the same strength performance from your design. Or you may have some special cellular materials, cellular structures, such that they will be absorbing more energy compared to the conventional design. Their thermal acoustic properties may be improved with the help of such special designs. Here you see an example. These are called mesostructured materials. And if you do not use such a case, obviously the weight of your product will be much higher compared to this new design. Or we can have such weird mesostructures, weird lattice structures in the design of parts for additive manufacturing. Here are some examples. You see a UAV, and they are trying to decrease the weight of it, since, as you know, in aerospace industry, the weight is a big challenge. They're always trying to decrease the weight of such flying vehicles. And lattice structures is a good example for that. There are many studies on such approaches. People are trying to decrease the weight of these products by using lattice structures. This is an example of it. And as I said, if you're interested, you can search for it and check some papers. We make use of these capabilities of additive manufacturing on the also industrial design side. Here, as you see, such kind of chairs, tables, some even dresses can be fabricated, some products, some lamps. So such weird designs, different designs can all be produced with additive manufacturing. You cannot have them with conventional manufacturing approaches. So you can have such customized designs for yourself. And the another thing is that people are all sharing these designs on different websites. These are from Cast3D, for instance. Even you can sell your designs on such websites. I have an account there. I put two designs, but not actually able to sell any of the designs. You can check myself on cast3d.com. Now we'll discuss another issue, but before that, if you have questions, we can discuss such design applications, design freedoms. Why do we need to do consolidation? How or have lattice structures? Any questions, guys? Okay, then let's discuss the challenges we have in the computer design side once you have these lattice structures or weird designs. So in such lattice structures, you have thousands of features. You have many little microstructures. They need to connect to each other. They have many troughs, beams, struts. So they will all increase actually the size of your files in the CAD software. And even if you have material compositions, that will be another challenge. You need to define the material of each region, each, let's say, cell or structure. And this will always increase the size of overall your CAD models. And sometimes you may need to have different physical and mechanical properties in specific regions. Again, that will be a quite burden on your design files. Here you see an example, for instance, people are using such lattice structures for textiles, and they have printed this one by using selective laser sintering. And obviously the size of this dress is maybe around some 100 megabytes. It's a huge number for CAD models. Here you see a kind of a dress. I think, as far as I remember, they printed it in SLS or SLA. Let's check it. Any questions, by the way? This is called as kinematics fault. You can see how they fabricated it. Since they are using many joints, such little triangles. So this is the compressed actually dress. So instead of using this huge volume, they compress it by 85%. Any other questions, guys, on this example?
Hocam bunları böyle üretip satan bir firma var mı şu anda?
I don't know, but probably not these days. Maybe in 10 years there might be such companies. It's quite expensive. You need to use lots of material. The time required is high. But some, I think, companies are doing some prototypes, manufacturing prototypes, using in some demonstrations. But right now, I think we don't have any commercial products, commercial companies directly printing such dress. Yes, Chata, you may give it a try, and in 10 years, we may be richer. So here you see, we have obviously many CAD systems, and these old CAD systems can be used in the modeling stage. And we are making use of feature-based modeling for most of the time. But if you want to produce some complicated things like dresses, you need to also do assemblies. And in these assemblies, you make use of some little structures together. And for the representation in this CAD software, we make use of constructive solid geometry and boundary representations at the same time. Since it's quite easier to do the operations on boundary representations, it's only responsible for representing the outer boundary of the designs. But in the constructive solid geometry side, the history is actually preserved, so you can have you can store how these designs, how these models are constructed. So that's why it's called as constructive solid geometry. And most of these softwares are using such an hybrid representation methods. And we said that in such complicated designs, such lattice structure cases, we have tremendous amount of information, and your CAD software, CAM or CAE software should be able to handle all these huge amounts of data. And in order to have a proper transfer between CAD, CAM, and engineering software, we need to use some standard files. The most common one is step files. With the help of them, we can exchange data between these software. But they're not obviously for the manufacturing. It's just for representing the geometry. And in some of them, you need to have extra files to represent the material throughout your design. And even, for instance, in such an extra file, you need to define these great interfaces between the regions. You may have smooth transitions, abrupt transitions. These are all stored, all defined in the material representations. This is an overall design for additive manufacturing approach. And here you see we have some steps. What we have a solution methods for design for additive manufacturing. And then we have a modeling stage. In this modeling stage, we try to model our design in implicit manner. Since once you have material distribution, microstructure, mesostructures, if you do explicit design, then the size of your file will be a huge one. So that's why we prefer to use implicit design. And then we need to do process planning. You need to do kind of a simulation to check whether it's possible. And while you are doing a simulation, you need to be aware of processes, the materials, the properties of other microstructures. And then if your simulation is fine, then you can do some little modifications. And lastly, analyze the code and do the printing. But at the beginning of your designing, you should be aware of this templates, the rules, the main rules for design for additive manufacturing. So now let's have a look at DFM and MFD. We already know about design for manufacturing. In this design for manufacturing, we have some burden limitations on the designers, but the manufacturing is fine. They have some specific machines, and once they are given the appropriate plan, they can complete the manufacturing. But what about manufacturing for design? So what do you think? Can we have such a paradigm these days, or do we need to still develop some other things, some other manufacturing technologies? What are your ideas? This is called manufacturing for design. Can anyone tell me what is the main difference between these two?
In the second one, there is a communication between manufacturer and the designer, and there's a feedback.
As this arrow is different, you're right. But what about, this is not the main thing actually I'm trying to ask.
Bireysel olarak birisi hocam, yani hedefe yönelik. Yoksa diğeri de genel bir.
No, in this one again we have a single person against single person.
Şey değil mi hocam? Başkası da konuştu. Siz buyurun hocam isterseniz.
Birinde dizayn için üretim şekline karar veriyoruz. Diğerinde üretim şekline göre dizayn yapıyoruz.
Yes, this is the main difference. In the first one, we have the limitations due to the manufacturing capabilities. For instance, your company may have just a milling machine, then your design should include milling processes. But in the manufacturing for design, designer has no, let's say, limitations. It has infinite freedom. They have infinite freedom, and they can design any kind of weird shapes. So they don't have any limitations in summary. But this time, the manufacturing side has some problems. But they need to overcome such problems by using maybe additive manufacturing or other novel manufacturing processes to actually respond to the needs of the designers. This time, as you see, the burden is on the manufacturing side.